So this is the Golden Gate Bridge. You might have seen it from, what was that show?
Friends.
Full House.
Opposite side of the country again. Opposite side of the country.
Who said Friends?
Friends.
I know it started with that.
It's 2,737 meters long, 27 meters wide. It seems small, but that's like 90 feet, and 227 meters high. It was an interesting, the time that it was constructed, because it was in the 30s, when it was a little bit tight, and people had a whole bunch of reasons to resist its construction. The Department of War said that it would block ships coming in from the San Francisco Bay, but they were just like making stuff up. The chief engineer was a guy named Joseph Strauss. It was actually, a lot of the work was done by a guy named Charles Alton Ellis, but they had a disagreement because it was taking too long, and Strauss basically kicked him out, and now he gets all the credit. I tried to find a picture of Ellis, but I couldn't, so you just have this guy.
All right, so basically I have the foundation, the introductory part of the project. My part is 3.1. So 3.1 basically speaks of equilibrium. Now equilibrium is not only the foundation of this chapter, but it's also the foundation of chapters to come. So equilibrium just basically means, is used to describe an object at rest, which can only be achieved by satisfying Isaac Newton's first law of motion. Now Isaac Newton's first law of motion was basically that, an object, a large object, had to come at rest, when a motion was acting on it. So that's where the equilibrium concept comes from. So here we see the formula we see all the time, coming to chapter 4, 5, 6, 7, and basically that's like the building block, and we build the different variations from that formula. Now, the Golden Gate Bridge is a suspension bridge. Now, a suspension bridge just basically means that the top part, the cable and stuff like that, it suspends the bridge from the bottom. So basically the reason why civil engineers use this method is to make the bridge carry more load, right? So, just think if you're like a civil engineer, for instance. You obviously want the safety of the people is paramount. Like you're thinking about cars coming through. You're thinking about traffic jams and stuff like that. Obviously, you want to have a good foundation, right? That's true. But why not have a strong foundation on the bottom and also a strong foundation on top and suspend it both ways? Using that equilibrium concept. Now this right here, I just want to talk about the parts of the Golden Gate Bridge. Keep in mind that the equilibrium concept is paramount. It's very essential. You're gonna use it in every single aspect. So for instance, here you have the main cables, which is the suspension bridge has the suspension aspect has two parts in terms of its cables. The main cables are worried about the horizontal aspect of the bridge. Now, okay, all right, fine. You get the horizontal cables, but now you want to suspend the horizontal aspect of the suspension bridge. So the way you reconcile for that is by having vertical cables to suspend that as well. So you have a suspension of a suspension of suspension, basically, right? So you have the main cables, the vertical suspender ropes. You have pylon, which there's different types of pylon 51, 52. You have the tower. Basically, these are all the main parts of it. And obviously, it's not my part to go into depth and to explain, the forces, how they cancel out. Roshni and Shirley, they're gonna talk a little bit about that. But these are just the main parts that are used for the suspension bridge of the Golden Gate Bridge. So, all right, so I want to talk about the disadvantages and the advantages. This is a really famous concept to use, for suspension bridges. But let's be real. There are some things that one has to take into account, especially people who are aspiring to be civil engineers, right? Now, let's start with the advantages. So, number one, if you wanna build a type of bridge, right? In this case, the Golden Gate Bridge is very long, right? I think you said how long is it?
It was
let me go back. It's fine. It's a long bridge, right?
Long.
So basically, the distance, the reason why it can be long is because the part before, just look at it, I think the saddle, I think it's called. You can go really high, right? So that the higher the tower is on top, the more further the cables can go. Therefore, the longer the distance of the bridge, right? So you have that advantage. You want to build a big bridge? Fine, do a suspension bridge. Now, it's very inexpensive to build. The materials are not that expensive. So that's really good. You know, you're a civil engineer, you're worried about, you know, you're worrying about labor, you're worrying about costs and all that stuff. You got to pay your workers. That's really good. You wanna consider that. And in this case, Joseph decided to do that. It's easy to maintain. You really, to maintain this concept, you know, suspension bridges after it's built, you really don't have to go out of your way to, like, you know, redo things, restore things, you know, restore materials. You can just go in there, just do some quick checkups, right? So in the future sense, you know, it's good, right? You're alleviating the workload of other engineers in the future. Now there's a couple of disadvantages, right? It's vulnerable to wind. You know, if you use common sense, obviously, like if you have a string and you just, you know, do it from here to here, you know, obviously it's gonna be like, you know, fluctuating from left to right. This is not a rigid body, right? So it's gonna be a little bit vulnerable. Now, not only that, but it's not gonna be able to really support high traffic. The fact that it's very flexible is an advantage and a disadvantage in a sense. And we're gonna see how it's an advantage later on. When you have a suspension bridge, you have these cables. Therefore, they're more suspect to be more flexible. That may be bad, but it also be good. It can also be good because that increases the margin of error, right? For example, later on, we're gonna see how this bridge had problems in its 50th anniversary. There was 800,000 people celebrating in the bridge. We're gonna get there. Like, it was too much. People were scared. Like, it was fluctuating from left and right. But Joseph, he was like, all right, listen, honestly, this suspension bridge is gonna be good because it's gonna widen the margin of error. So it can fluctuate from, you know, from 55 feet or 55 meters or no, 55 feet or like vertically or like 15 feet horizontally. You know, it's fine. It can fluctuate. The margin of error is fine. And that's exactly what happened. We're gonna see that later on. Now, this right here, it takes a long time to build. Despite the fact that the materials is inexpensive, it takes a long time to build. So therefore, it'll still end up being expensive, right? So it really, you gotta pick and choose your poison, right? It really depends. All right, so this is what I was talking about, historical issues. On the 50th anniversary, they expected, if I'm not mistaken, 50,000 people. They expected 50,000 people. You know, you're a planner, you're a mayor, I guess. You know, you obviously have to understand all these concepts, right? Understand the load of the bridge. You're like, all right, you know, we can expect 50,000 people. Well, 800,000 people showed up, all right? They showed up, and look how crowded this thing is. So what was going on is that not only were there 800,000 people, not only was the load, you know, incredible, but also the winds were contrary. They were like boisterous, you know, they were just like really like, you know, bothering, you know, the bridge, you can say, right? And basically, people were worried. They're like, yo, like, I don't want to say yo, but they were like, we're gonna die, right? But basically, one of the engineers, he was like, Joseph, don't worry about it. Joseph thought about this. He understood the suspension bridges. They're very flexible. You know, the margin of error is wider, and they said, well, you know, the bridge, you know, was designed to move 15 feet vertically, up and down, and 27 feet from side to side. All right, so that happens. It fluctuates a little bit. Don't worry. You know, nothing. The bridge is not gonna come down. All right. Now, I just want to talk about a brief history of bridges with suspension. This is just some interesting facts. The first modern example of this type of bridge were in the 1800s. All right, that was the first, you know, the most recent ones. Now, if you go even more back, a guy by the name of Fang Tong Wanpo, he was from Tibet in China, right? It was a province in China, and he built a lot of suspension bridges in the 15th century. And basically, you know, he built. Oh, sorry, let me finish. This right here is interesting. I don't know if this is true or not. I wanted to look at who came up with this idea. And it is said that people were observing monkeys, swinging from vine to vine, and they're like, oh wow, like the vine is suspending like the weight of this monkey, and he's basically like going from vine to vine. Let's implement this concept to a bridge. So that's it.
So now there is like two assumptions that's made from the first thing. That's the one is that there is the only gravitational load. The vertical load is already taken by the vehicles and the people that are going on. And the second one, that these cables are parabol because it can take the more load on that. Now the force of suspension. The force of suspension is like there is a two suspenders for one. If I took the back slice, there is a two suspension, and there is a one back slice that's going on a down. So each suspension get half of the load from the deck slide that you can see. Only a half of the load is taken. So it is more balanced from the downward and from the upward. Just go ahead. Now it has in a main cable there is a tangent, so it has a lot of bunch of the pin, and each pin has a different force because of their orientations are different, angles are different, so it's changing up, but they try to balance it from the suspender to here, and there is two force. They have it on a same distance from the both ways. They have it the same force at the same time. So it's more. They think about to the balance the pin, the orientation and angle is changing suddenly, and when it goes to the let's go to the next. To go to the anchor range, it will it has the pin has a lace force, and it just goes to the anchor range. So anchor range is a main factor for this kind of bridge. So it is quite heavy, and it has a force like a force side, so it could be stable to the chair, and it can be stabilized the whole bridge. It's have it a horizontal. It has a force of the pin. There is a fraction force, normal force, the anchor range. There's a force that's on middle, and that's why it is quite heavy. So it can be balanced the whole bridge and pins. Yes, right.
Okay, so analysis of loads and load sharing in general. So when building a bridge, we need to consider the weight, the environment, and the load types of the bridge. So this is very important because these are also the forces that can be applied on the bridge. Next. So the dead loads, like they mentioned it before, it's everything is the bridge itself. So it's weight, the cables, the cement, and everything that is just right here. So it's called dead load because it doesn't move. Then the live loads is the traffic, the cars. This moves, and it's based on the number of trucks, the number of cars, and everything that people, everything that passes through the bridge. The dynamic loads, these are the outside forces that cannot be accurately measured, like the wind, vibrations, and the extreme weather. Load relieving techniques or load considered. So existing bridges are expected to carry traffic and increase in loading, and a lot of stuff can change, like population and the weather and stuff like that. So they need to enforce the bridges, and one of the ways is it's the deck bending relief by external pressing. So this pretty much, this is, okay, so it's a conventional pressing for a bridge deck. It imposes in a permanent direct compression together with a bending moment which counters and applies the dead load moment. So for example here, in this bridge in France, we have the three like triangles, which is like the stronger shape. And this holds the bridge for like to make it stronger if it depends like if it has to carry like more weight or like heavy loads.